Hi, my name is Mandy Xia, and I'm a PhD student at Cornell University. Today, I'm going to talk about our work, a wave optics-based fiber scattering model. This is joint work with Bruce Warder, David Bindel, and Steve Marshner from Cornell, and Eric Michielsen from University of Michigan. To realistically render fiber materials, including human hair, animal fur, and cloth, graphics researchers have developed many physically based fiber scattering models. These existing models are all based on tracing rays through fiber geometry. However, for many kinds of fibers, especially small animal fur fibers and textile fibers, their sizes are comparable to visible light wavelength. On this slide, I'm showing a scanning electron micrograph of a nylon fiber cross-section, and you could roughly compare it to visible light wavelength on this slide. At this scale, wave effects such as diffraction and interference are more obvious, and ray optics is no longer a good approximation. In our work, we present the first wave optics-based fiber scattering model that models missing effects in ray-based methods. I will tell you about our boundary element method-based wave simulator. We use it to simulate electromagnetic waves interacting with a cylinder, and from the simulation, we compute an azimuthal scattering function. Conducting full wave simulation is very expensive. We make the computation more tractable by making use of the symmetry of the problem and compute 3D electromagnetic fields using only 2D cross-sectional slice. We integrate our wave-based model into a modern rendering system. I will explain how we handle this integration and why the naive integration will suffer from energy issues. We demonstrate that our model can reproduce a wide range of fibers with different sizes, cross-sectional shapes, and material properties, including textile fibers, animal fur, and human hair. Ray and wave models produce different results. We examine the similarities and differences between ray and wave predictions. We will show that the wave results include strong color effects due to diffraction and interference, softening of sharp features, and strong forward scattering that are not predicted by ray-based methods. Before going into our method, let me briefly give some background. We consider each fiber independently and construct a bidirectional curve scattering distribution function, abbreviated as BCSDF, to characterize how light scatters on the fiber. We assume that all the fibers are locally straight of uniform cross-section so that we can model them locally as homogeneous infinitely long cylinders. The translational symmetry of the problem causes light to reflect specularly into a cone, removing one dimension from consideration. Therefore, the infinite homogeneous cylinder scattering problem can be computed using a 2D calculation involving the cross-sectional shape of the fiber. The resultant function is called the azimuthal scattering function. Following the original Marshner model, most fiber scattering models assume the separation of azimuthal and longitudinal dimensions, and apply a longitudinal blurring function to account for the irregularity along the cylinder axis. We adopt this assumption and replace the azimuthal scattering function with a wave optics one. For the longitudinal component, we apply the energy conserving function from Eugene Dion's work. Wave optics is the theory that studies light propagation as electromagnetic waves. The middle is an animation showing diffraction, which is bending of waves around the corners of an obstacle into the region of geometrical shadow. The animation on the right shows interference, where two waves superpose to form a resultant wave of different amplitude. Now let me talk about how the wave simulation is performed. Instead of tracing rays, we conduct a full wave simulation to compute the fields produced by scattering an incident wave. This slide shows an example of an incident wave coming from the left, sweeping across a cylinder cross-section from the bottom to the top. Introducing the fiber alters the fields, and we call the resulting fields the total fields. The animation on the right shows the total fields after introducing the fiber. Different computational methods can be used to solve the scattering problems. Compared to other numerical methods such as the finite difference time domain method, the boundary element method only needs to discretize the boundary of the fiber cross-section, which has lower complexity, lower memory cost, and higher efficiency. So we apply the boundary element method to solve our problem. The presence of the fiber divides the space into two regions, denoted as region 1 and 2 respectively. In region 1, which is free space in our problem, the total fields can be further written as the sum of the incident fields and scatter fields. These fields satisfy Maxwell's equations, and the tangential component of the fields need to be continuous on the boundary of the fiber for energy conservation. This PDE problem is reformulated into a set of boundary integral equations where we can make use of the boundary element method to solve numerically. We introduce fictitious currents as intermediate quantities both on the outside and inside surface of the scatterer. We make use of the surface equivalence principle, which states that any fields that exist in a source-free region can be generated by some surface currents residing on the boundary of that region. This principle lets us transform the scattering problem into a pair of problems concerning unbounded homogeneous media. In the equivalent exterior and interior problems, we can express the fields as integration of the surface currents multiplied with the Green's function, and this formulation is called the source-field relation. This relation enables us to compute the scatter fields once we know the surface currents. Next, we make use of the boundary conditions and relate the incident fields and the surface currents via the boundary integral equations, and solve for the currents using the boundary element method. The boundary element method discretizes the boundary of the cross-section and turns the boundary integral equations into a matrix system to solve. After we obtain the surface currents from the boundary element method, we can replug them into the source field relation and compute scatter fields. With the scatter fields, we can compute far field scattering intensity. Please refer to the paper for more details. The general approach of applying boundary element methods to solve scattering problems is not new in computational electromagnetics, though we apply this particular formulation that is specialized to the problem of dielectric fibers and derive the equations for this problem. Now it's time to think about how to apply what we obtained from wave simulation to render fibers. Due to the differences between ray and wave optics in nature, special treatment is needed when integrating such a wave optic scattering function into a path tracer. The naive way of integrating the wave fiber model would result in excessive energy, as shown in the furnace test renders on this slide. The reason is that the incident power in the wave sense is larger than what a path tracer collects. The illustration on the right tries to show that there's light bending due to diffraction that is considered as missing rays in the ray model. Thus, the effective cross-section in the wave case can be larger than the geometric cross-section. To account for this, we conduct proper normalization when computing the scattering distribution, and we propose to enlarge the geometric cross-section at intersection test to achieve energy balance. On this slide, the third image shows that the new wave optics render conserves energy. To summarize the algorithm, we conduct wave simulation for different incident directions and wavelengths, average over two polarizations, and tabulated the Azimuthal scattering function. At rendering time, we interpolate the tables to compute the Azimuthal function, and together with the longitudinal function, we can compute the full BCSDF and render fibers. With all the description of the method, now we can take a look at how ray and wave predictions compare to each other. Here we plot the azimuthal scattering functions for non-circular cross-sections used in our work. We show the normal incidence lines and compare the ray plots in the first row to the wave plots in the second row. For each subplot, the x-axis and y-axis are incoming and outgoing azimuthal angles respectively. We integrate the scattering function over wavelengths to obtain RGB representations. We observe rainbow colors in the wave plots, but not in the ray ones. Compared to the ray-based functions, the wave simulation produces much smoother distributions for non-elliptical cross-sections. Plotting a 1D slice in the third row, we can clearly see that the wave optics predictions, as represented using the orange curve, has stronger forward scattering peak. These differences in the azimuthal functions will manifest themselves in the following rendering results. On this slide, I'm showing a spiderweb iridescence example. A is a photograph of such effect. B is rendered using our wave optics-based fiber scattering model. C is rendered using the previous ray-based method. Our wave model is able to produce strong color effects with similar hue shown on the photograph, while the ray model only produces a colorless render. This scene contains an elliptical curly black hair under an environment light and an area light. The wave result produces softer and brighter highlights on the edges of the model, which can be observed from the backlit scenarios. These figures showcase an animal fur rendering. The hamster fur is textured using 6 different kinds of elliptical fibers with different color. The wave results has softer highlights and has more overall translucency. This figure shows a sofa scene where the top surface of the sofa and the side surfaces of the 3 cylinders are made of silk. The highlight predictions are different, and the highlight of the wave predictions is stronger. Our wave-based model is able to produce missing effects in the previous ray methods. This is a first step towards more general wave optics-based fiber scattering functions, and there are exciting future directions we would like to pursue. Our current work makes use of 2.5D wave simulation, where the cross-section is in 2D and wave has 3D characteristics. In the future, we would like to generalize the current model to a full 3D wave optics model. The challenge is that the computation rapidly becomes very expensive. We consider each fiber independently. This assumption also applies to conventional ray-based methods. However, when the scatterers are close together, the interference between scatterers can play an important role. The third direction is to save wave simulation time and storage cost. Currently, for an irregular cross-section, we need a few gigabytes to store the azimuthal scattering function. In the future, we would like to explore the structures of these distributions and potentially make use of neural models to fit to these distributions and compress the tables. In conclusion, we present the first wave optics-based fiber scattering model that comes from a full wave simulation. The ray and wave models produce similar appearance for complex fiber assemblies under some conditions, but the wave predictions include strong color effects due to diffraction and interference, softening of sharp features, and strong forward scattering that are not predicted by ray-based models. We would like to thank Zechun Zhang and Francisco Monticon for their helpful discussion on the project. We also thank Sitian Chen for generating the woven pattern used in the sofa scene, and Lingqi Yan for letting us use the converted hamster scene. We would also like to thank Under Armour for providing the textile sample.